Okay, so thank you. So this is the last talk of the first part of this series. Okay, so what I would like to do is try to end the story that I have begun on Monday. Okay, so let me. In the beginning, I've given many proofs and many detailed things. Today, I think there will be some sketches, but it will be essentially, well, you'll see. Okay, so let me first sum up what we've done up to now. So let's assume that gamma is a non-elementary word hyperbolic group. Mu will be a probability measure on gamma, which is symmetric with finite support such that it generates gamma. And so what I try to do is to translate probabilistic features into geometric terms and try to bypass probability and use geometric methods to solve problems. Okay, this is a little the theme of using this green metric. Okay, so the first thing well, not the first, but what we showed is that if you look at the identity map from gamma ds to gamma endowed with a green metric, then this is a quasi-isometry. Okay, moreover, gamma dg is a hyperbolic space. So from this, we were able to deduce that the Martin boundary of gamma was the same as the Gromov boundary of gamma with a word distance, with a green metric, which is also the same as the Gromov boundary of the group with any word distance. Okay, and what we saw also is that, but unfortunately I did not give a proof. If I have time by the end of the lecture, maybe I'll do that. That I could identify the asymptotic entropy of Avez with the drift in the word metric of this. And we also noticed that mu is a quasi-conformal measure on the Gromov boundary of the group coming from the green metric. Okay. And what else? Okay, so this is essentially what we did. Okay, so what sort of consequence can we get from that? So maybe, so I might have been, when I stated the theorem of Cornert and Peterson-Sullivan, I don't remember exactly what I said about the Radon-Nikodym derivatives, so I would like to just make sure that we agree. So if gamma acts on some space X geometrically, on some hyperbolic space geometrically, and you denote by rho to be a quasi-conformal measure. On the boundary, then when I pull back rho by G, and I evaluate its Radon-Nikodym derivative at a point A at infinity, then this is essentially e to the v, the Boozman function at A of my base point W, G minus 1 of W. Okay? The way the quasi-conformal measure is constructed, it is associated to a base point as was explained to us yesterday by Linshu. So here, implicitly, this one is a rho sub W measure. That's why W appears in the Radon-Nikodym derivative. Okay, so you see that for harmonic measure, what we had, it is exactly the same formula, but with an equality, and so it was e to the Boozman function for the green metric. So here I need my point A on the boundary, times E G minus 1, I think. Well, it should be that, because it is a conformal measure. So from this, what I deduce is that the volume growth in the green metric is 1. Okay? Because there's only one dimension possible for the quasi-conformal measure. So here, this is an instance where I don't need to do probability to deduce something. Okay, but good. So now, is there any question? No, okay. So what do we know? We know much more about quasi-conformal measures, and what is really important when we want to make estimates is to use the so-called lemma of the shadow. So let me remind you that if X is hyperbolic, and you take it you take your favorite base point inside. Then if you consider a point X in X and some radius R, then I will define the shadow of seen from W of the ball of radius X, of the ball centered at X of radius R. It will be the set of points A at infinity, such that there exists a geodesic ray which intersects the ball. Okay, so what you have to have in mind is something like that. So here you have X, and you look at all the balls like that. Okay, so what you obtain is something like this. This is the shadow. So sometimes it's useful to consider the shadow also inside the space, but from what I want to do, it's not that important. Okay? And so basically what do we know on this shadow is that if you have a point inside the shadow, then we can have a control. So when you have a geometric action on X, then for any X R bigger than some constant R0, which only depends on delta, what we know is that the shadow will be approximately a ball. So saying that there exists a constant which depends on R, such that, and a point A in the boundary, so that if you look at the ball centered at A, so this is in the visual distance with parameter epsilon of radius 1 over C e to the minus distance from W to X is contained in the shadow. and it contains the ball, and it is contained in the ball centered at A of radius c times e to the minus the distance from W to X. So shadows is a very nice way of trying to translate information inside the space to infinity and vice versa, because we have a very strong relationship between what is going on the two. Okay, so what is important here is that it only depends on the distance to the base point. Yes. Okay? So to prove this, you just approximate by trees and work it out. And so what does the lemma of the shadow say? It says that if rho is a quasi-conformal measure of dimension v over epsilon, then there exists some R0 such that each time I fix R bigger than R0, the measure of the shadow of seen from W of the ball centered at X and of radius R is approximately, so here the constant depends on R, but if we fix R once and for all, it won't depend, it will be a universal constant. And this is e to the minus v times the distance from W to X. Okay? And this is what we use to prove that quasi-conformal measures are Hausdorff measures. And because it gives you exactly the right scale, you see that this is approximately, this is essentially the ball centered at A and a radius e to the minus epsilon. Yes, here I forgot the epsilons everywhere. The distance. And so what you see is that the measure of a ball of radius r is essentially r to the power v over epsilon. So now I can apply it also for the green distance and the harmonic measure. Because if I want to work with a green metric, I will use the fact that I have this identity mapping which will map geodesics here to quasi-geodesics which behave well. So then this will give me a notion of shadows. And actually the shadows are the same because when you take the image, if R is big enough compared to the quasi-isometric constant, what you obtain is that the image of the shadow will be another shadow for the green metric too. Okay, and the radius, it will be different, but since it will be a uniform constant, then it won't depend on the constant. And so what I get to is that the harmonic measure of the shadow seen from W will be equivalent to E minus the green distance from W to X. So exactly the same shadow, I have the same estimates once I fix R big enough. And this comes just from hyperbolic geometry. Okay, so this idea of trying to compare the harmonic measure with, to get such a formula already appears in the work of Kaimanovich in a paper in '94, I think, in Quell's journal. And so what sort of consequences can we get? So we get some deviation inequalities. Okay, that I will quote now. So first, what you can show is that the probability that Zn of W, that the distance from Zn of W to the ray W Z infinity is at least a distance d. This will decay exponentially fast. So this says that with with high probability, you're close to the geodesic. So this is, in some sense, an asymptotic Ancona inequality that we obtained. Because in Ancona inequality, this was just the walk at the first time, and we had here a finite time in between. But there we go up to infinity. A second thing is that what I explained to prove that the space was this metric space was hyperbolic is that the quasi-geodesic were quasi-ruled. Remember that, meaning that I could control the Gromov product. And so here what we get is that the trajectory is also quasi-ruled, but in average. So if I look at the Gromov product of Zm of W and Zm plus K plus L or N of W seen at Zm plus K of W, this is bounded by some uniform constant. B is a positive constant. Yeah, delta, everything, all the delta, I guess the support, the quasi-isometry constant, which depends themselves on the support of mu, and everything is quantitative. Yes. Well, actually, the random walk, I see it in the group, and then I make the group act on W, on the space. And so another deviation inequality that we obtain, yes?
So that last one, that tau zero is independent of M, K.
Yes. No, it's just a Markov property that you use. It's always, okay. So let me say the last thing. So the last thing is an improvement of what I said when the random walk is how does it shadows another almost sure convergence thing. So which says that the limit of the distance from Zn of W to the geodesic ray over log is zero on mu almost surely. Well, it's zero almost surely as n goes to infinity. And so just let me comment on. So you deduce these two things from that one, okay? And this one, essentially, the idea, I won't give the proof since I said I was not giving many proofs today, is that you look at the point where you land at infinity, and you pick any point and you assume that it is at distance at least d, okay? So then you pick a point x here where it is exactly d. And so what you see is that z infinity is in the shadow seen from Zn of W cast by the ball centered at x. Okay? And this is where the exponential comes from, because it's a quasi-isometry, this d here, it becomes a big distance also in the green metric. And once you have that, so you want to prove something like this, what you do is you try to compare where the points fall in the geodesic, in which order, and then you cut the things into little pieces and you compute each estimate. Because you have this exponential decay, then everything gets finite. And this is Borel-Cantelli, as usual, when you want to get something almost sure. And there is a last consequence that I will use soon, which is of different order, is that if I look at mu on the boundary of x with a visual distance coming from from x, then this is a doubling measure. Which means that there is this constant C and alpha, such that for any R bigger than R, so I take capital R and little r two radii, and so for any x, if I look at the ball centered in the visual distance at any A in dx, centered at A of radius capital R, divided by the mass of the same ball at the same point but of radius little r, this is bounded by the ratio of the radii to some power alpha. Okay? So usually it's stated saying that twice the radius is bounded by a constant, but this is equivalent. This is exactly what you get when you make some exponential towers, a telescopic thing. Yeah? And so this comes from the fact that we have also a quasi-conformal structure at infinity. And the quasi-isometry that I have over there gives me a quasi-symmetric map. And because the measure nu is alphos regular for the visual distance in the green metric, it translates into the doubling condition afterwards. And so this is very interesting because it means that, no, this is for nu actually. This means that the measure behaves well with respect to the visual distance. Even though it can be singular to the Hausdorff measure, it always behaves well. Because this is a good way, good starting point to make analysis on this metric space, to have such a measure. So it behaves somehow a little bit like the Lebesgue measure, and we have some good control on that. Okay. So now I would like to proceed. And so the theorem I would like to state is due to Tanaka. So assume X is proper and hyperbolic. Gamma acts on X, and its relative volume growth is finite. Then pick a measure mu with finite first moment. So let me check the assumptions because this is not my theorem. That's it. Then, if I look at the limit as r goes to 0 of log of the harmonic measure of a ball centered at A of radius r compared to log of r, this is equal to h over epsilon L. Okay? And so this means that the dimension of the harmonic measure is h over epsilon L. So what is the dimension of a measure? It is the infimum of the Hausdorff dimensions of set Y of full measure. Okay, so I look at every Borel set, and I want to look at the smallest which carries all the information of my measure. And so what I get is h over L. So this formula is the formula that you get in dynamical systems, which was found by Lyson-Jung, Le Drapier, Jung, etc. This is the entropy, and this is like a Lyapunov component. Okay? And also what we know is that the dimension of the... Okay, so when the group is hyperbolic, and I have a good quasi-conformal measure, so corollary, if gamma is hyperbolic, then you recover the Ghosh inequality because V is just the dimension of the boundary. So of course, the dimension of a measure which lives in a set is smaller than the dimension of the set itself. And so this is some sort of real inequality somehow that we saw yesterday. And so I would like to sketch. So Tanaka has several statements where he covers several things. He does not need to have proper, but then he needs some strong assumption on gamma and stuff like that. What I would like to do is just sketch a proof in a very simple case. So when gamma acts on X geometrically, and when dg is hyperbolic, so support finite and symmetric. And when X actually is itself. That's what I mean. I let it act on its Cayley graph, just because it's a little, it doesn't make much difference. But actually, with what I said, it's fine to use X. So what we want to compute is this, right? And so the idea is to look what's happening with shadows. So I want to compute the limit of the shadow seen from W of Zn of W with some fixed radius R over the diameter of the shadow. And then I need to take logs, because otherwise it's not the same formula that I obtain. So what is this limit? Well, the mass of the shadow, I know it because it's given by the limit of the shadow, right? So this is minus the green distance from W to Zn of W, essentially. So here I need a limit. And what is the diameter of the shadow? Well, I told you it's given here with a distance in X. So this is minus epsilon, the distance of W to Zn of W. So in X. Okay? And so now you can do the little trick, which is you divide by n on top and below. And what do you recognize? You're supposed to recognize the definition of the drift. So this is exactly LG divided by epsilon L. But then we've seen that the drift in the green metric was exactly the entropy. So this is it. Okay, so I would like to say, so then I'm happy and I'm done. But this is not true because here I need to compute the ratio at the same point. So what I'm doing when I'm looking at shadows, so I have my point Z infinity here, W, but my Zn of W is somewhere there. At best, it will be log n close to my geodesic. So I'm not looking at a pointwise limit. And so to be able to use, to go from this limit to the limit I'm looking for, which is that one, I need to control what's going on at this point, which we called pi n of z infinity in the theorem of Kaimanovich. And to make this control, this is where we need to use the doubling condition there. Because we have this doubling condition, we know that we can move around a little the board as long as I can control the ratio of the radii. So even though it's a little O of n, it is still working because the little O of n will disappear with the logs. Okay? So it's a little harder than what I thought, but still it works well. It's a one-line proof somehow, with some technical details behind. but which is fine because we have the doubling condition. Okay? And so now, my starting problem was to understand this inequality when it was an equality. So I can rephrase this question in terms of geometry, fractal geometry, if you want, geometric measure theory, saying, what happens if I have a doubling measure which has maximal dimension? So, okay. So now it's a geometric condition. It's no more something very abstract that I had some numbers which were coming from different places. And so, do we have examples for that? Well, actually, we have, because in the example of the, so, examples of equality. So the first example is the free group with the example that I explained on the second course. So we have gamma equals the free group with a uniform measure. Uniform measure for mu. Because in this case, we saw that the green metric was proportional to the word distance, and so everything is just the same, essentially. So both conformal measures agree, and so there's no problem. So now, maybe you don't notice, but if you endow gamma with the green distance, there we also have equality, because the entropy is equal to the drift times the volume, which is equal to 1. Okay. So this always holds. It's kind of stupid. But, and then there's another set of examples. Discrete. You can define random walks from Brownian motions by making some discretizations. So this idea of discretizing Brownian motions into random walks goes back, I think, to Furstenberg. So Jean-François complained that I was not saying Furstenberg enough. So now I'm trying to emphasize this is a great guy. And so the idea is you have a manifold given by the quotient of its universal cover by gamma, and you assume that it has finite volume. And you look at the Brownian motion there, it is recurrent. And you can put in place a way of a stopping time argument to build a random walk on the group gamma. So in this case, you obtain a symmetric random walk mu. The support of mu is the whole group, but it reflects the properties of the Brownian motion. So if you know something about the Brownian motion, then you can transfer it to the random walk, and vice versa. They have the same harmonic measure at infinity. They have the Green functions are proportional. The drift are proportional. Everything is proportional by the same factor. So if n tilde is a symmetric space, then we know we have equality for the Brownian motion, and then we get equality here too. N tilde symmetric space, rank 1 symmetric space. And look at that. Okay? But here you see I have infinite support because it's the whole group. And so the question is, are there other examples? So essentially, what can I say when it is finitely supported? Because I know that with infinite support, I have some conditions. And here, this is not a genuine example because it is a very abstract metric space that I don't control in general. This is some sort of abstract nonsense, if you want. It just means that the green metric is really what behaves the best with respect to my random walk. And so the theorem that I want to quote is due to Guézel, Mathéus, and Lecourant. It says, so I will set it into two settings. So I assume that gamma is word hyperbolic, and I look at it with a word distance. So then, the first statement is that for any finite set sigma in my group, there exists a constant, and for any measure mu with support, So for any finite set sigma, there exists a constant C, which depends only on sigma and the group, if you want, smaller than 1, such that for any probability measure mu, the support of which is contained in sigma, H is strictly smaller than C times LV. So it means that given the support, you can never attain equality with the word distance. So here, this is crucial. And the second one, so they have more things in their paper, of course. And here, see that I don't care whether the support generates the whole group or not. Even I don't know what the group will be. I don't know if it will be quasi-convex or if I can apply the machinery there. It's completely general. So there are several cases they study to get to that. Yes? Unless if gamma is not free. Non-virtually free, sorry. Thank you. So it means that the only case which remains is essentially this example. Yeah, sure. And the second is that if you let mu n be a uniform measure on the ball of radius n, then h of mu n divided by L of mu n tends to V. Okay, so if you take bigger and bigger measures, which are uniform, then you go to the so then it reflects the topology, the geometry of your space in some sense, asymptotically. Okay? So in the time that I have left, so let me tell you that, okay. So I would like to give some ideas of this statement when I assume that sigma generates the group. Mu is symmetric. Everything is symmetric here. I'm sorry, I forgot the symmetric assumption. And try to explain where it comes from. Okay? So I don't want to show that I have a constant smaller than 1, I just want to get the strict inequality. sketch when support of mu generous gamma implies and gamma non-virtually free implies what? H strictly smaller than LV. So it relies on a previous result that was established by Blacher, Mathieu, and I. So here you assume that gamma is word hyperbolic. I don't know if the supremum over all sigmas which are of given cardinality is bounded. The thing is, maybe you can use... yes, because I have many different measures I can put inside. You just change the weight. But then you can try to concentrate, you can try to be clever, for instance. The way you define mu to maximize the... So it does say something more than just saying that it is an equality. There's a gap, which depends on the set. Gamma word hyperbolic, non-elementary as usual, mu finite and symmetric. Then the following are equivalent. H is equal to LV, to rho and mu have the same measure sets. 3, the rho and mu are equivalent, meaning that the ratio is bounded by uniform bounds, far from 0 and infinity. And the last one is that the identity map, I will set it like that. If I look at the distance, at the green distance from x to y, minus the distance in the group times v, this is bounded by a uniform constant. So saying that I have a 1c quasi-isometry. Okay, so I claim that these 4 things are equivalent. So what is supposed to be easy is to go from 4 to 1. Okay? When from 1 to 2, this is where it demanded us the most work. Okay? And this question we could ask, if I replace the harmonic measure with any other conformal measure which comes from a different action, and I know that it has maximal dimension, does it imply this? I don't know. Okay? This is, to my knowledge, this is open. But maybe some thermodynamic formalism will do the job. I don't know. Because actually we use very strongly the fact that we have some structure of the harmonic measure, which comes from probabilities. So we cannot get rid of all the probability, even if we can state things geometrically. Maybe it's reassuring for the lectures for the school. Then to go from here to there, what I use is a substitute for the geodesic flow and ergodicity, which enables me to get some uniform bounds. This is not very difficult as soon as you have the material. To go from there to here is just the lemma of the shadow. Once you control the Hausdorff, you show that the Hausdorff measures are the same. Essentially, it means that you came from the same matrix. That's what it says. And so now, oops. So I know we have to take the pictures, but can I have, maybe I need a little more time, maybe just to explain the basic idea. I think that there's something interesting to still that I didn't say it. Okay, so I'll try to be quick. So one case which is easy, so to prove this theorem, they use this property. Okay? So if C is 0, then this is very easy. Because then what you're saying is that both metrics are proportional, And what do you know about the word distance? It takes only integer values. So the Gromov boundary of gamma, we know is the same as the Boozman boundary because this is the Martin boundary. And the Martin boundary is the same as Boozman. And so this is totally discontinuous. This is totally disconnected. Okay. So then this implies that gamma is virtually free. Okay. So now what happens if C is non-zero? Well, we need to kill C if you want to make something, right? So how do we get rid of C? Well, we try to take some asymptotics data instead of just working directly with the sets. Okay, so the idea is to introduce the translation length. So let me remind the definition. So tau of G will be the limit of G to the n divided by n. Or let's say in my E to the G n divided by n. Okay? And so from this, what you obtain is that tau of G in the green metric will be equal to V times the translation length in the word metric. This is how, because you divide by n, the C will disappear in the end. Okay, and so what do we know when we work in the word metric? Yes, it's the stable length. It's not the translation. Okay, so stable length. Yeah, maybe I'm wrong on the vocabulary. I'm sorry. So what do we know in the case when you work in the word head, in the word distance? Well, we know that all these numbers, they form a discrete subset of n, of R is a discrete subset. So I suppose this is Gromov, because when I don't know who it is from, it must be Gromov. Okay, and the idea is that everything is integer valued, and so you make a combinatorial argument, and you see that you remain at a rational. Actually, you get a rational with bounded denominator. Okay? So to get a contradiction, we want to prove that in the green distance, when gamma is not virtually free, then this set of translation length is not discrete. Okay? So I would just add a word to say how do we get to this thing. So this is called being non-arithmetic. The spectrum is non-arithmetic. So this is well known for surfaces, for instance. So there are several ways to prove such a statement, to prove non-arithmeticity. And so in the paper, what they do is they use co-cycles and some Lifshitz business, and well, they use dynamical features, but I thought it's not very geometric and does not correspond to what I'm trying to explain to you during these lectures, that we can do a lot of things with geometry. So there's another way to get to that, is to use cross ratios instead. So this is an idea of Dalbo. But for this, we need some good properties of the green metric. It turns out that it satisfies what is called a strong Ancona inequality. So normally I have less than 5 minutes and I'm done afterwards. I'm sorry, I know we have to take the picture. What? Oh! No, that's fine. Then I can make a fool of myself. Very good, maybe I'll even finish on time. I'm sorry. Okay. I'm trying to wrap up to go. Okay, so what are those inequalities? So this was established. So in the finite support case, this is due. So this is why I need my notes, because to Izumi. This is the name Neshveyev. Neshveyev, I think. And Okuyasu, I think. So this is for finitely supported, and when you have super exponential terms, this is Guezel. So the thing is, in their paper, I didn't really find the statement I'm going to give, but it should be easy to deduce it from their work. But it's well, okay. But in Guezel, it's very explicit. And so, what does it say? It says the following. There exist constants L and lambda such that for n R0, for any R bigger than R0, for any points x, y, z, w in X, such that the distance of the geodesic from X to Y to Z to W is at least R. So the picture is like this. Okay? Or whatever you want to draw it, but it is. So here I said that this one is discrete. So to get to a contradiction, I need to show that it is not discrete. So that's what I want to explain the basic ideas to prove that.
They use the next
Yes, they use that. So instead of that, they use a Boozman cocycle, which they evaluate at some points, and then they make some continuity argument. So in both cases, if you assume that it's arithmetic, you get a continuous function, and so it has to be constant, but it's completely absurd to be continuous, to be constant. So then, so with the Boozman function, you try to relate the Boozman cocycle at the attracting point to the repelling point. And so this is where you need a non-trivial component to have a loxodromic element inside. And so to be able to show that they have some co-boundary, they need a sort of Lifshitz theorem for that. Okay. But so this talks to experts, but otherwise I don't know. So that's why I prefer to make another argument. So they say in their paper, oh, I'm sure we can use Dabo to do it, but we have a more direct proof. Okay, so I looked at the proof, I don't know. Then it's really a matter of taste. For me, it's more direct to do what I'm going to say. In any case, in both cases, you need this. Ah, I did not know that. For cat 0, okay. But here we're in a hyperbolic. It's so what I'm going to say is that actually the green distance for finitely supported or super exponential tail is almost like a cat -1 metric. This is what I want to explain now. And so they have this thing, so they compute. So you look, so it is already some sort of cross ratio. That's why I think it's more natural maybe to, okay, so what's the, so you look at the green distance function from x to z, or z, times y to w, and then you divide this by the green function from x to w times the green function from y to z, I guess. You subtract 1, and this is smaller than L e to the minus lambda r. Okay? So this is very technical, and there's no way I can make the proof. And even reading it, I didn't find a good, well, whatever. But here, this is essentially the log of this thing. And the log of this thing, this is essentially the green distance, the cross ratio of this distance. Okay? This is essentially cross ratio in the green metric. Okay? Because when you take a log of a number which is small, the log of 1 plus something small, it is the thing small, right? And so here what it says, for instance, is that what does it say? Well, it says a lot. So let me explain. So here I don't know if... So I will rely on a work of Nika and Spakula, I think. So one of your colleagues, right? Bogdan Nika, no? He's no more in Göttingen? Ah, you don't know him, okay. Spakula. What I prove is that under this assumption, so thanks to the work of these people, the Gromov product in the green metric extends continuously to the boundary of gamma with the green. Well, we don't care because they are the same. To the Gromov boundary of gamma, and moreover, there exists an epsilon positive such that when you look at d sub epsilon equal to e to the minus epsilon, the Gromov product, so this is for points on the boundary, this is a distance. Okay? A genuine distance. Okay? And so it follows from the fact that we know that the green metric is hyperbolic, and we have this very good exponential control. It is equivalent, actually, in some sense. Okay? So this is exactly what's happening for cat-1 spaces. Okay? So it means that this metric is very nice when it's finitely supported. And so in particular, what we will get, what's not difficult to prove, is that we get exact formulas as if I was in a cat-1 space. When we work in hyperbolic metric spaces, usually everything is up to some multiplicative or additive constant. And there they all disappear. And from that, the idea is to say that, is to relate. So this is an idea of Dalbo, or maybe Otal. But I learned it in a paper of Dalbo, in any case. Okay. They relate the... So what she's done, she did on... it was on surfaces, I think. maybe of constant curvature, but I don't know to which extent it's very important. But the idea is the same, is that because she's using estimates of Bourdon and cat minus one stuff. So what they show is that when you look at the cross ratio of 4 points, this belongs to the exponential of the subgroup of the length spectrum to the closure of the length spectrum. So to prove such a statement, first you do it for 2 fixed points, for 2 pairs of fixed points which are disjoint, where you can make some sort of explicit computations. So first step is fixed points, pairs of fixed points. Okay. And then you make a continuity argument. The continuity of the cross ratio. So it's the cross ratio with this distance. And so if your length spectrum is discrete, then the subgroup will be discrete. But you see that the cross ratio is not, it cannot be constant on a non-trivial component. Okay. So then you get your contradiction. And so as I said, so in the paper of Guezel, Mattheus, Moucourant, they say that you can do it like that, but they think it's easier to use the co-cycle. So they project the co-cycle on R over Z. There they solve the Lifshitz co-boundary equation, and then they go on top, and they get their continuity argument in a non-trivial component. Okay, that's how they proceed. So now I have some time left, right? So there are 2 things that I can do in 15 minutes. I can try to sketch this proof, which is, I think, could be, I don't know. Maybe it will show you that it's hard, the argument that we have does not apply to Patterson-Sullivan measures. And I can also try to sketch the proof that asymptotic entropy is equal to the drift in the green metric in the simplest case. You prefer that one? Okay. So I need my notes. Okay, but otherwise, yes, so maybe before that, I should say that, you see, we work with the word distance, and the reason why we don't have equality seems not to be very natural somehow, because we have this discrete set. So if I look at, for instance, a surface group acting on H2, we don't know. It's completely open. So maybe that's the... As soon as we don't have this discreteness argument, we don't know how to conclude. So somehow it is a little disappointing to have such a result, because we don't see... well, of course, we use some geometric facts, because to be discrete, to have a discrete length spectrum is very strong. But it is also very specific. So open question. So I will just state it in the case of Fuchsian groups, but it's the same in other situations. So let gamma be a co-compact Fuchsian group. Mu finitely supported probability measure. So you look at gamma acting on H2. Does it imply that H is more than LV? We don't know. Okay? the best we can do is exactly what they did. Okay, so what I would like to prove, or to sketch, I mean, is the fact that if nu and rho are not equivalent, then H is smaller than LV. Okay. So that it relies on several lemmas. So first I will define some random functions. So I will set phi n. It will be rho of the shadow at Zn. So I will work in the group, but you can work also on a group acting geometrically on a wet hyperbolic space. It doesn't make any difference. But that way my, so R will be always fixed, so I forget capital R. But the fact that it is a shadow is important, I guess, because otherwise we don't know what we consider. Right? Okay, and I'll define this, and phi n will be the log of phi n. Okay? And so I have 3 lemmas. It seems that I'm doing everything I can to be late, but it's not true. Huh? So the first, it's not the right set of notes. There is a constant C1 such that when you look at the zero mean of the expectations of phi n, this is bounded by C1. So this is independent of n, otherwise it's not very interesting. Okay. 2, there is a constant C2 such that when I look at the expectation of phi n plus C2, this is subadditive. And 1 over n of phi n tends to H minus LV. This is the capital phi n, this one. And this one is the little one. And the third condition, the third lemma, is that the little phi n tends to 0 in probability. So for every positive alpha, the probability that phi n is bigger than alpha tends to 0. So let me comment a little bit on these statements. So first, what we know, because of ergodicity, is that if nu and rho are not equivalent, then they are totally singular. Okay? So what I expect is that this goes to 0 almost surely, for instance. But this is not true because it's the same problem as when I computed the dimension of the harmonic measure. These things are not centered at one point, so I cannot use the differential Lebesgue differentiation theorem, which holds in my setting because nu is a doubling measure. Okay, so this cannot work. So this is a little why we have to do all this thing. So this is just a brute force computation. Okay, you write what it means, then you exchange the order of summation, and you use the fact that it is rho is you use the fact that they are conformal measures, but there's nothing very special. For that one, it's the same. It's essentially because you get to you apply the you apply the lemma of the shadow. And so each time when you take the log of these things, what you see is that log rho is essentially the distance in your space, and this is essentially the distance in green metric. And this is the best we can do, saying that they are totally singular. So we need to use a doubling condition to make sure that we get what we want, but we cannot get better than that. Okay? That's what I thought. Okay. So the proof goes as follows. So I fix an eta small enough. So it has to be at least smaller than 1 over e, but it will be even smaller, I guess. And then I set an to be the event when phi n is at least eta, and bn the complement. Okay, so what I know from lemma 3 is that if n is large enough, then the probability of Bn is at least 1 minus eta, right? Because this is the probability thing. And so this means that when I look at the expectation of phi n, dp, on Bn, this is bounded by 1 minus eta log of eta. So this is very small. Okay, that's the point. And now I want to compute the same thing for an. And here I will use Johnson's inequality. So this is smaller than pi of an log of phi n of a dp divided by dp an. Okay? And so this I have a bound which is, I can show that it is always small. So it's smaller than e log of 1 over eta. So here I can even take plus eta log plus of the expectation of phi n. Okay? And so the thing is that thanks to lemma 1, I know that I can find P very large so that the expectation of phi P is at most twice C1. Okay, because otherwise I wouldn't get an upper bound when I take the César mean by C1. And so this implies that the expectation of phi P, it is at most 1 minus eta log of eta plus something big O of eta. Or big O of 1, I don't know, I don't care. Or big O of eta. Okay, and then, no, it's not eta, it's eta log eta. Little O of 1. And now, so since this is as negative as I want if eta is small enough, so pick eta small enough so that this thing plus C2 is at most minus 1. And then I'm done thanks to the subadditivity. Okay. So the idea is what? So I want to look at 1 over k expectation of phi of k times p plus C2. Because it is subadditive, this is smaller than p times no, this is smaller than the expectation of phi p plus C2. Okay. And this is smaller than -1. Okay. So now I divide everything by p. And I let k go to infinity. And so it is strictly smaller. And so this is, so you see here, to prove these lemmas, we really use the structure of random walks. And that the harmonic measure is not any measure I'm looking at. And to tell the truth, you can construct by hand on the interval 0, 1 a doubling measure of dimension 1, which is totally singular with a Lebesgue measure. So the idea is you need to put weights. So you take your interval, you cut it in several pieces, and you put weights in such a way at each scale they are more or less the same. But when you go down below, you diverge, but at the same time you control the Hausdorff dimension of the thing. Okay? So here, geometric, so when we started, we thought that, oh, that's very good. So we have conformal measures, so we can apply stuff. We have some doubling measures, so we can apply analysis. But it turned out that it was not that clear, that we didn't have any general theorems which we could apply directly, and that we still had to use all the strength of the structure coming from harmonic measures. So to conclude, so what I've tried to explain, what we tried to do with Blacher and Mathieu was to say, we have this green metric at hand. What can we say about the random walk if we know something about the green metric? No? And so what happened is that we were able to prove some certain amount of theorems, and here it was useful for Guezel, Maucourant, and Mathéus. I don't know why I'm having trouble with the alphabetical order. But in general, most of the results that we proved were improved later on by using better machinery than what we did, which is very good. And that's it. So thank you for your attention and for your patience during all this week to listening to me. Yes. Mm-hmm. So there's a very nice paper of Ballman and Le Drapier where they explain how this works. I think this is where the simplest place I found. So the idea is that you pick two concentric balls in your manifold. You start your Brownian motion and you look when you come back in the smaller ball and you don't, when you touch the smaller ball. And once you go out, you flip a coin, something like that, huh? And with some Bernoulli probability, which is not 1/2, but something which comes from the geometry of your manifold, you decide whether you make it a stopping time or if you continue. So if you stop, well, you stop. If you don't, well, you wait for the next, it goes back. And then you play the same game. And it turns out that what you get is a Markov chain, which comes from, provides you a random walk. And because everything comes from the Brownian motion, it is related to the green function. And the flipping of the coin is independent of. I cannot hear you. I'm sorry. Yes, because you see, if you lift your Brownian motion to the universal cover, when you go back to this ball, actually you're going to a translate of it. So this defines a probability to go to some element of your group. I think you should use the microphone, huh? Because.
So you're going to ask. So you're going to partition the universal cover by the translate to the fundamental domain, and then ask when it stops.
Not even, yeah, somehow. But actually, we just look at the orbit of these balls, which are pairwise disjoint in the universal cover. So it's not a genuine partition, it's just a local, local thing. And as I said, so Bellman-Le Drapier, it's a seminaire SMF. So I've sent this morning a little late a list of references to Mahan, so who's supposed to forward it to somebody else. And hopefully, if I see... and that reference is inside. So I've tried to order the reference by general readings, things on Martin boundary and green metric, things on discretization, things on dimension formula. So dimension formula, I think the first one who looked at it was maybe Kaimanovich in a paper on trees. And then there was a paper, there's a very influential paper of Le Drapier on free groups. Actually, it's a small lecture notes at Montreal, where most of the things that he did maybe 16, 18, or 20 years ago, we tried to copy in the word hyperbolic settings afterwards. And there's also a section on discretization and some other references that we use, for instance, where to find a version of the section theorem that I used, the paper of Dalbo, and stuff like that. So it's maybe not complete because I did what I could, but hopefully there's enough reading to. And also a section of relatively hyperbolic groups, which I didn't discuss, but which is a hot topic right now. And which is, the ideas that they use for relatively hyperbolic groups are really the same ones as those. But more complicated, so that's why it's better to...
So, other questions or comments? No? If not, let's thank Peter for very generous to give us 4+1 talks. Thank you.
Thank you.